Take a good look at this. It's a pretty sloppy-looking 3, right? And it's on a super low-res 28 by 28 pixel grid. But your brain? It knew what it was instantly. For us, this is just easy. But now imagine you have to sit down and write a program to recognize it. Suddenly, that simple task feels almost impossible. So, how do we actually teach a machine to see what we see so effortlessly? Well, let's dive in and find out. In this explainer, we're going to peel back the layers on neural networks. We're going to get past all the buzzwords to really understand what it means for a network to learn. And it's not science fiction. It's actually a surprisingly elegant piece of math. All right, so here's our roadmap. We'll kick things off with that recognition puzzle. Then we're going to build our own digital brain from scratch and figure out the language it uses to think. From there, we'll watch how it improves itself. This is the cool part, before we hit a pretty surprising reality about what's really happening under the hood. And then we'll wrap it all up with the key things you need to know beyond all the hype. Okay, so back to our puzzle. The thing is, our brains can see 1,000 different handwritten 3s. Some are loopy, some are sharp, some are tilted, and we just know they're all the same idea. But a computer doesn't see an idea. It just sees a grid of numbers. And from its point of view, all those different 3s look like completely different grids of numbers. That's the challenge. So here's our mission. We're going to build a network that can take in 784 pixel values. That's one for every single pixel in that 28 by 28 image. And its one and only job is to light up one of 10 possible outputs. It has to give us a confident answer for every digit from 0 all the way to 9. To pull this off, we can't just write a bunch of rules. We have to build a structure, a kind of digital brain. So let's look at the basic building blocks and see how they all fit together to get us from raw pixels to a final answer. And the most basic unit of this brain is the neuron. Now, it's really important not to get too hung up on the biological comparison here. For our purposes, a neuron is just, it's a thing that holds a number between 0 and 1. We call this its activation. You can think of it like a little light bulb. If the number is close to 0, it's dim. If it's close to 1, it's burning bright. That's it. That's all a neuron is. Okay, so our network has layers. The very first one is the input layer. It has 784 neurons, one for each pixel, and their activations are just how bright each pixel is. Simple. The very last layer is the output layer, with 10 neurons, one for each digit from 0 to 9. Whichever one is the brightest, that's the network's final answer. And then, sandwiched in between, we have what we call hidden layers. In our case, we've got 2 of them, each with 16 neurons, and their job is to try and find meaningful patterns in all that pixel data. So how does the information actually move from one layer to the next? It's all about the connections between these neurons, and every single one of those connections has a kind of knob on it that we can tune. Now get this, in this relatively simple network we're talking about, there are almost 13,000 of these adjustable knobs and dials. That's the real scale of the challenge we're facing, figuring out how to tune 13,000 different parameters just to get the right answer. So let's talk about those knobs and dials. In the world of neural networks, they have specific names, weights, and biases. And they are the fundamental language the network uses to learn and to change its mind. The idea here is actually pretty straightforward. Every connection between 2 neurons has a weight. Think of it as how much influence one has on the other. A big positive weight means if the first neuron lights up, it strongly encourages the second one to light up too. And then each neuron also has a bias, which is just a number that says how likely is this neuron to light up in the first place. These thousands of weights and biases, they're the only things we can actually change to control the network's entire behavior. Okay, so we've got 13,000 knobs to turn. How in the world do we know which way to turn them? Well, that brings us to the actual learning process. And it turns out it's a lot like trying to find the bottom of a valley by always taking a step in the steepest downhill direction. First things first, we need a way to know when we're screwing up. This is where something called the cost function comes in. It's basically a way of telling the computer how wrong it is. So when the network sees a 3 but its output is just garbage, the cost function spits out a really big number. When it gets it right, it spits out a small number. You can think of it as a lousy least score for the network, averaged out over thousands of different examples. And here's what that actually looks like. On the left, you've got a high-cost situation. The network is totally confused. The output is a mess. On the right, that's a low-cost output. It's confident, it's correct, it's lit up only the 3 neuron. The entire game of learning is just about tweaking all those internal knobs to reliably get from the mess on the left to the clean answer on the right. So, this is it. This is the crucial question. How do we systematically adjust all 13,000 of those knobs to get from a high cost to a low cost? How do we find the one magic combination of settings that actually works? The answer is a brilliant algorithm called gradient descent. Now try to imagine the cost as a kind of landscape. If we only had 2 knobs to tune, it would be a simple 3D landscape with hills and valleys. But we have 13,000 knobs. So this is a mind-bending 13,000-dimensional landscape. Gradient descent is basically the process of dropping a ball at some random spot on that landscape and just letting it roll downhill. Using a little bit of calculus, the computer figures out the steepest downward slope from any given point and takes a tiny step. You do that thousands and thousands of times, and eventually, the ball will settle down into a valley, a set of weights and biases that gives us a very low cost. Okay, so the process works. The ball is rolling downhill, the cost is getting lower, and the network's answers are getting more and more accurate. But what is it actually learning inside those hidden layers? Is it learning the things we hoped it would learn? See, our hope, our really elegant theory, was that the first hidden layer would learn to recognize simple little things, like short edges or curves. Then the next layer would learn how to combine those edges into bigger patterns, like circles or long lines. And finally, the output layer would piece those patterns together to form a whole digit. It's a beautiful, intuitive idea, right? And here comes the twist. For this kind of simple network, that beautiful, intuitive idea is completely, totally wrong. It is not what is happening at all. On the left, that's the dream. The network learns clean, understandable parts of a digit. But on the right, that's the reality. When we actually look at what the neurons in the hidden layers are searching for, it's not neat little edges. It's this jumbled, chaotic-looking mess of pixel patterns that makes absolutely no sense to a human eye. The network found a valley in that 13,000-dimensional space. It just wasn't the nice, tidy one we were expecting. And this brings us to the really big picture. For any student of AI trying to get past the hype, what are the key takeaways for understanding how these systems really operate? Okay, first, learning isn't some kind of abstract magic. It's just the mathematical process of minimizing a cost function. Second, gradient descent is the engine that makes it all happen. It's how the network finds its way downhill. Third, and this is so important, a network can get the right answer for reasons that are completely bizarre and uninterpretable to us. And finally, just because a network gets really good at one specific task, that does not mean it has anything like general intelligence or true understanding. And that kind of leaves us with a final big question to think about. Our network learned to recognize digits, but it didn't learn the idea of a digit the way a person does. It just found a weird mathematical shortcut that works. So if machine can be right for reasons that we can't comprehend, or for reasons that just feel fundamentally wrong, what does that tell us about the nature of understanding itself?